Welcome to week 5. So in the last week, we have seen how to design a low noise amplifier, which is the first stage in a receive chain. Now we are going to look at how to design the mixer, which is going to take input from the LNA and then it is going to feed to channel select filter for further signal processing. So we know that the way we have defined that mixer is just a multiplier. So it takes, let's say, a voltage signal at RF frequency, multiplies with the LO and generates a voltage at IF frequency. So we are interested in a multiplication functionality from this block, which can do the multiplication in time domain. Let's say we are given these two voltages and we want to multiply two voltage quantities. So this is similar to trying to design a gain block where we know that the VIF is going to be A times VRF, but we can make this gain to be a function of LO. So if we can design some block like this, we will be able to implement this multiplication of two voltages. And this gain need not be actually some amplification. It can as well be an attenuation. So as long as the attenuation is function of VLO, we will be able to implement this multiplication operation. This attenuation is much easier to design as compared to a variable gain, because we can do is we can just take two resistors like this and apply VRF, and let's say this R1, R2, both can be varied by VLO. So this VIF, which is R2 by R1 plus R2 into VRF, can give rise to product of VLO and VRF. For that to happen, we can make sure this R2 is a linear function of VLO and this R1 plus R2 is some constant which doesn't change. So let's call it R total, where R total is equal to R1 plus R2 is a constant. So if this happens, then we can say that the attenuation here is a linear function of VLO, and as a result, we can implement this multiplication using such a simple resistor divider. This is simple multiplier using a resistor divider in resistor. Okay. We will see that when we are talking about designing this mixer in a CMOS process, we'll find that it is easier to design a current source than a voltage source because these MOSFETs act like a voltage controlled current sources. So there is a motivation to implement this kind of multiplication in the current domain, where we have this RF signal in the current domain, for example, like this RF, and now we need to implement a multiplication. And if we take the analogy from this voltage division, we can similarly here also implement a current division with the help of just passive devices. So say we have these two conductances G1 and G2. If you look at, say, this current IIF, you can see that this IIF is equal to G1 by G1 plus G2 IRF. These are conductances. Can be controlled by VLO. So this G1 can be a function of VLO, and G1, G2, their summation is always constant. So let's call it some G constant into IRF. IIF is a product of VLO and IRF. This K and G constant are some constants. Here, G constant to G1 plus G2. So if G1 increases, G2 reduces so as to keep the sum constant. Now, the way we see here, the most critical blocks are these voltage controlled conductances. And it turns out that in a CMOS process, we can easily design this voltage controlled conductance with the help of MOSFET. So we can design this circuit by replacing this G1, G2 with, let's say, these transistors M1, M2. And we need to bias these transistors. So let's say some V bias is added so that both of them are operating in saturation. And on top of this V bias, we can apply this VLO. And since we know that we want to keep the sum of these two conductances to be constant. So when we increase the VLO on one side, we can reduce VLO on the other side. So if this is, let's call it as IIF1, we can, first of all, we can make sure the M1 and M2 are biased in saturation to act like voltage controlled and on top of this bias we are applying plus VLO and minus VLO so as to control their conductances in equal and opposite manner. So we know that it's looking in impedance. Here is 1 by GM1. Here it is 1 by GM2. So to find out IIF1 is going to be equal to GM1 divided by GM1 plus GM2 into IRF. And let's say GM1 is having a nominal GM of GM0, and when we are applying this VLO, its GM is changing by some KVLO. Similarly, GM2 is having a nominal transconductance of GM0, and when we are applying minus VLO, its GM is going to change by minus KVLO. So in such a scenario, we can write it as GM0 plus KVLO divided by 2GM0 IRF. Now it is half plus K by 2 GM0 to VLO IRF. You can see that we are able to implement a circuit which can perform the multiplication of these two quantities. But there is this extra constant term which is not required. Okay. This is easy to solve. What we can do is we can observe this IF2 as well, and we can already see that because of symmetry, every time this IIF, let's say, increases because of IRF, this IIF2 is going to reduce. So I can quickly write down IIF2 as half minus K by 2GM0 VLO into IRF. So if I have a way to take difference of these two currents, I can see that this half term will vanish and I will have just K by GM0 VLO into IRF. So a differential current output will be just a function of product of these two quantities scaled by a constant. So we can modify the above circuit and perform this difference by converting these currents into voltages. Let me also add a MOSFET in saturation to convert the VRF into IRF. This M3, take VRF and get IRF, which is GM3 into VRF. E V by S plus VLO by S minus VLO. Instead of taking these currents and trying to subtract them, we can convert this current into voltage. Say VIF1, VIF2. Define a VIF, which is a difference of VIF1 and VIF. So very easily we can see that this VIF, which is VIF1 minus VIF2, is RD times IIF1 minus IIF2, which is in turn equal to this constant K by GM0. And here also we can see that IRF can be written in terms of VRF. So I will put everything together. This will be GM3 RD to constant K by GM0 into VLO and VRF. This is the scaling factor. So we have got a circuit which is using these three transistors, and this differential output is a function of product of VRF and VLO. So one important point to note here is that this circuit acts like a generic multiplier. So as long as, in our case, this, for example, this conductances and transconductances are acting in a linear manner, we can see that this circuit will be giving a generic multiplication operation. But if we look closely at our requirement for wireless system design, so in our case, wireless systems find that mixer generally has one input as a carrier or local oscillator signal. And this carrier or local oscillator signal has all the information in its frequency or time period. There is no useful information in the amplitude of a carrier or local oscillator signal. So, information in frequency or time period. And the amplitude is only a scaling factor. So higher the amplitude, higher will be the output product. but it is not going to contain any useful information. So the amplitude is the scaling factor. So based on this, what we can do is we can try to see if this VLO amplitude can be maximized, so that if we can maximize this VLO amplitude, we can maximize the strength of this VIF product. It turns out that for square law set, maximum VLO swing at which complete steering of current takes place is given by VLO to be equal to root 2 by 2 of VGS or 2 minus VT when it is biased at this V bias voltage. What this means is if the VLO, should say VLO peak if it is equal to this value on top of the V bias, then the entire current will be steered towards M1 and M2 will be going in cutoff. Okay. So beyond that, if we apply VLO, there won't be any use. So the maximum VLO which we can apply will correspond to this situation when entire current goes to either M1 or M2 while the other branch is cut off. So let us call this as VLO max. So when this VLO max is applied, such a scenario, this entire current will be coming from here and M2 will go in cutoff. So applying VLO max maximizes VIF. So this is a really useful situation, and we can see that if a VLO is a sinusoid, then periodically we'll be steering current either towards the M1 side or towards the M2 side. So if we take this VLO signal, so if I plot this VLO of time, let's say it's a sinusoidal signal. What we are saying is this should correspond to this VLO max. Okay. And when that happens, you will see that we are assuming the GM1 and GM2 to be a function of VLO. So because of this large signal being applied at the gate, these GMs are going to change very fast. So if we only look at, let's say, this current in the one branch, then we know that this depends on GM1 divided by GM1 by plus GM2. Now for small swings of VLO, this term changes linearly, but since here we are trying to maximize the LO swing, it turns out that this coefficient also becomes nonlinear. But at least we know that at these peaks, this coefficient will become close to 1, because at these positions, the entire current is going to flow into one other branch, and on the other side, the current is going to completely steer towards the other branch, so this current will become 0. So this part is known to us, and because of this non-linearity, this plot looks like this. So this coefficient is toggling between 1 and 0. And this is definitely, there is a nonlinear relationship between VLO and this coefficient. But we are interested in only maximizing the product at the IF. So for that reason, we are allowing nonlinearity to take place. So if we look at the frequency spectrum, VLO is having single tone if it's a sinusoidal wave. Single tone, let's say low. Whereas the actual coefficient which is going to appear in the expression for the VIF is going to have a lot more harmonics because of this distorted waveform. So this GM1 by GM1 plus GM2 is going to have, say, something like this. So there will be a fundamental tone, and you add omega LO. But in addition to that, it is also going to have, you can see, there is a DC value. This is going to be there. Then because of this half wave symmetry, it is only going to have odd harmonics. Here at 3 omega LO and something at 5 omega LO and so on. Next due to abrupt switching of F1 and to simplify the analysis, we can approximate this waveform for GM1 by GM1 plus GM2 as a square wave. So this is estimated to square wave And now we can use this approximation to find what is going to be the final IF output. So we can simplify the circuit by replacing those MOSFETs with switches which will turn on and off when LO signal is applied. E, D, and here we can say we are applying some periodic signal LO. Here we are applying complement of this LO. This LO bar looks like. So this is the LO. LO bar is this. And the idea is whenever this LO is high, the switch is turned on. When the LO is low, switch is turned off. In such a scenario, if we have to find this VIF1 and VIF2, see that this VIF1 is going to be equal to this IRF, which is being multiplied by this square wave, which is when the switch is turned on, this IRF will appear as it is at the output. When the switch is turned off, there is no current here at the output. So it's like multiplying this IRF with a square wave. Let's call it P of t. P of t is going between 0 and 1. So this LO and LO bar are the switching signals, so deciding when the switch is turned on and off. And P of t is just a square wave which goes between 0 and 1. You can simplify this by writing this P of t as sum of its frequency components. So we can see already it has a DC term 0.5 plus it has a fundamental with a strength of 2 by pi sine omega L O t. This is happening at T LO is equal to pi LO plus for this 50% duty cycle square wave, we'll be having third harmonic 2 by 3 pi P harmonic and so on. Okay, let us look at the frequency spectrum to understand which all frequency components are going to appear at the desired IF frequency. So if I have to draw the spectrum for this P of t, it is going to have its fundamental, has a DC, then it has a third harmonic, and then fifth harmonic, and so on. This is the frequency spectrum of this P. Now let us look at the frequency spectrum of this IRF. IRF is going to be concentrated around the omega RF frequency. And for our analysis, let us take example of direct conversion receiver, where the omega RF will be equal to omega LO. So this is your IRF. Okay. Now, when this product happens in the time domain, it is going to create, it is going to result in convolution in the frequency domain. So this product will, for example, the fundamental of P of omega at omega LO will translate this the signal at RF to baseband. It is going to result in signal like this. Okay. It is also going to result signal at 2 omega LO, because omega RF is equal to omega LO. It is something like this. What about this extra terms which we are getting as a result of this nonlinearity? So it's 3 omega LO and 5 omega LO. So they are also going to come into picture. For example, this 3 omega LO term is also going to create its own component. This 2 omega LO. And then there will be some component which will appear at this 4 omega LO and so on. But if we observe the useful component at the IF, in our case, the IF frequency is same as the DC frequency, is going to be only coming from this fundamental. Okay. And all the other spurious components are going to be away from this desired baseband frequency. So if we apply a filter this, it is going to get rid of all the other spurious components. So these are going to be yes. So they are going to get filtered out, and we will be having only our desired signal, which can be further processed by the VGA and the ADC. So let us try to find out what will be the strength of this VIF1 around the IF frequency, which is DC in our case. So VIF1 around omega IF will be equal to, you can see, the strength of the signal at around RF will multiply with this 2 by pi sin omega LOT. So half of it will be appearing at the DC and half of it will be appearing at the some frequency. So this is going to be half of 2 by pi, whatever is the strength of IRF, multiplied by RD. So here also we should multiply RD. by RD. This is equal to by pi. IRF is GM times VRF. GM3 into RD VRF. So if I take the differential output, VIF at omega IF is going to be difference of these two IF voltage, which is equal to twice of this value, 2 by pi GM3 RD VRF. So if I define a gain as the ratio of desired signal at the IF frequency divided by the input signal at the RF frequency, then this gain is going to be equal to 2 by pi GM3 RD. This is also called as conversion gain. So a mixer has a conversion gain because the input and output signals are not at the same frequency. In our case, we are getting it to be equal to 2 by pi GM3RD, which is much more than 1. So this is also called as single balanced active mixer. Circuit which we have discussed is called as active mixer, and this case where we have only the differential LO being applied. So with respect to the LO, it is having a balanced port. For that reason, it is also called as single balanced. So this is a single balanced active mixer. So the case when we have RF also available as a differential signal, then we can modify the circuit to allow differential port for RF as well as LO, and that is called as a double balanced active mixer. So when this VRF is applied and LO is on, signal goes in this manner, IRF. We can see that since we also have access to minus VRF, this minus VRF is going to create signal in the opposite direction. So what we can do is this plus IRF, which is flowing in RD, we can allow this minus IRF to flow into the other R, so that when the differential output has been taken, we get a twice output. For that reason, this is connected here. Here. 2, 4, 5, 6. These are your switching quad. And now we can see that all the times either IRF or minus IRF is flowing into the output load. This is called as double balanced active mixer. Easily find the conversion gain. CG2V is the differential output VIF here. With respect to the differential input VRF. And if we take this ratio, VIF divided by differential input, which is 2 VRF, it is going to be equal to 2 by pi GM 5 RD. So this conversion gain is similar to what we got for the single balanced case. The advantage here is we can apply a differential RF signal. And also, you will see that if you look at each of these IF ports, so each of these IF ports are asymmetrical with respect to the LO, because both are having one connection from the VLO as well as minus VLO through the MOSFET. So when we take the difference, any coupling because of the LO signal to the single-ended IF will get cancelled, and we have no artifacts because of this LO swing getting coupled to the drain of this switching quad MOSFETs. After understanding the conversion gain of single and double balanced active mixer, now let us try to understand how to analyze noise in these kind of mixer circuits where we have MOSFETs with time varying behavior.